Hi, in this video we are going to talk about red-black trees, so let's get started. What's the motivation behind balanced binary search trees, AVL trees and red-black trees? For example, we want to construct a binary search tree from a sorted array. We have an array 1, 2, 3 and 4 and we keep constructing our binary search tree. The first item is 1, it's going to be the root, 2 is greater than 1, 3 is greater than 1 and it's greater than 2, so it's going to be the right child of 2, then 4 and so on. So we ended up with a linked list, and the operations time complexity for a linked list is linear, and we try to make logarithmic. So that's why we have to make sure that our tree is balanced. So the running time of binary search tree operations depends on the height of the binary search tree, so we should keep the tree balanced in order to get the best performance. In an AVL tree, the heights of the two child subtrees of any node differ by at most 1. Another solution to the problem is the so-called red-black tree. So AVL trees are faster than red-black trees because they are more rigidly balanced, but needs more work. So operating system relies heavily on these data structures. And that's why it's good, because if we use AVL trees and red-black trees, then the operations such as insertion, deletion, and the search operation for a search tree is going to be logarithmic, no matter whether it's the average case or the worst case complexity. So we have red-black trees properties which have to be met. We are not able to violate these properties. So what are these red-black properties? Each node is either red or black. This is why it's called red-black tree. The root node is always black. All leaves we represented with nils are black. Every red node, must have 2 black child nodes and no other children. So it must have a black parent as well. Every pass from a given node to any of its descendant nil nodes contains the same number of black nodes. So these are the red-black properties. And this is a typical red-black tree. The root, the 13th node, is black. Every red node has 1 or 2 black children. Every red node has 2 black children, and that's why we have to use these nils or null pointers not to violate this property, because if the leaf node is a red, then with the help of these nils, the red-black properties are not violated because these nils are black colors. So every red node has 2 black colors. Yes, so this is a typical red-black tree. And of course, if we want to make sure that these binary search trees are balanced, no matter we are talking about AVL trees or red-black trees, we have to make rotations. These rotations, by the way, are very efficient because they can be used several times. These rotations are the same for AVL trees, these rotations are the same for red-black trees, and these rotations are the same for splay trees. So the rotation operation itself is the same. So we can make a right rotation or a left rotation, and this illustrates how the subtrees are changed. And we just have to update the references, which can be done in constant time complexity, and that's why these rotations can be done very, very fast. And as you see, the in-order traversal is the same, so the rotation doesn't change any property of the tree. So for example, the in-order traversal of the left tree is A, X, B, Y, C. The in-order traversal after the rotation on the right tree is A, X, B, Y, C. So it is the same. So it's very important that we can do any of these rotations and the basic properties of the tree will not change. And by the way, it is very fast. We can do it very, very easily with these rotations. We just have to update the references. So every new node we insert is red by default. We are going to see a little illustration, it will be clear. We keep inserting new node in the same way as we have seen for binary search trees or AVL trees. So if the node we want to insert is smaller than the root, for example, we go to the left. If it's greater, we go to the right. This is the basic principle of a search tree. On every insertion, we have to check whether we have violated the red-black properties or not. If we have violated the red-black properties, we have to rebalance the tree and we have to make rotations, or we just have to recolor the nodes. We have 3 cases, and because of symmetry, we originally have 6 cases, but 3 of them are the same. So in case 1, we have the X node, and we have a black root node. The root node has a left red child and the right red child, and the left red child has a right red child. This is the X. And of course we have the subtrees A, B, C, D, and E. The problem is symmetric, so we have to apply the same operations if we are dealing with the right tree, whatever. So we come to the conclusion that the uncle of X is red too. The uncle is the other child of the grandparent. So the X parent is the left child of the root, and the other child of the root is the uncle of X. And we come to the conclusion that the X we are dealing with is red, and the uncle is red too. So we just have to recolor some nodes. It is quite easy case. We don't have to make any rotations, we just have to recolor it. And as we can see, the X is now the root node, so we just have to recolor some nodes. It's quite easy case. Plus the X will be the root node in this case. And why is it important? We will see in the example, the concrete example, that with the help of this recoloring, we may come to the situation where we again violate the red-black properties and we have to make some further, for example, rotations or again recoloring. So it's quite a recursive operation that we keep recoloring, then checking again whether it is a red-black tree. If it's not, we have to make, for example, rotations. After the rotation, is it a red-black tree? No. Then we have to make some recoloring or rotation. So this is just a basic case. It is kind of subproblems. So these are the subproblems, and if we know how to deal with these kinds of problems, we just have to apply these until we get to a valid red-black tree. So we have to check recursively from bottom to top whether the red-black properties are violated or not again. Yeah. The case 2, as you can see, that the uncle is black. The uncle of node X is a black node, plus the node is a right child. It's very important that the X we are dealing with is a right child, because it's the right child of the parent. Okay, the uncle is, this is the uncle, it is black. So we have to make a left rotation on the node X parent. This is the parent, this blue one is the parent of node X. We have to rotate the blue node, we have to make a left rotation. If we were dealing with the symmetric case, as we have discussed earlier, then we would have to make a right rotation accordingly. In this situation, we have to make a left rotation on the blue node. And after the rotation, we end up with this situation. And again, we have to check whether the red-black properties are violated or not. This is just a subproblem. As we have discussed, a red node is forbidden to have another red child. So maybe if we come to this conclusion, we have to make other operations such as recoloring or rotations. We are going to talk about at the end of this video. There will be a concrete example. It's going to be clear. But these are kinds of subproblems, and we get to know how to deal with these little subproblems to be able to solve the whole problem itself. Okay, the case 3 is when the uncle of node X is a black node, and node X is a left child. In case 2, the node X was a right child. No, it is a left child. And in this is the uncle, of course. And here we have to make a rotation on the X node's grandparent. The grandparent now is the root node. The grandparent, of course, is the given node's parent and its parent. So the parent of parent is the grandparent, of course. I think it's pretty straightforward. So here we have to make a right rotation of the grandparent. And after the right rotation, we come to this situation again. And of course, it may be the case that after this operation, the red-black properties are violated again. Then we have to apply one of these cases. Recoloring, so these are the subproblems, case 1, case 2, case 3. With the help of these operations, we are able to make a red-black tree valid again. So let me show you an example. We have a red-black tree like this. This is a valid red-black tree. Okay, I forget to color the gray nodes to black because I want to assign numbers to it. So the gray nodes are the black nodes, whatever. And this is a valid red-black tree. The root of the tree is black, and all the red nodes have 2 black children. What about the leaf nodes? As we have discussed, the leaf node has 2 nil children which are black. I don't painted them, but all leaf nodes have 2 nil black nodes. Okay, so we want to insert 12. As we have discussed, inserting into a red-black tree is the same as inserting into a binary search tree, which we began at the root node. 12 is less than 32, so we go to the left subtree. 12 is greater than 10, so we go to the right subtree. 12 is less than 19, so we go to the left. And 12 is less than 16, so we inserted the left child of 16. And as we have discussed, every new inserted node has color red. And we come to the conclusion that, okay, we have inserted our node, so we have to check whether the red-black tree properties are violated or not. And it is violated because the node 16 is red and its children 12 is red too. And in a valid red-black tree, every red node has 2 black children. So it is not good, and we come to the conclusion that, okay, it is violated because the red node has a single red child. And this is the case 1 situation, as you may consider. We just have to recolor the nodes because the node X now here is the node 12, and the uncle of 12 is red too, and the 12 is a left child, so we have to make some recoloring, and we made it. Okay, so we have to check again whether the red-black tree properties are violated or not. That's what I'm talking about, that after making this operation, we are not okay, because we see that with the recoloring operation, the red-black tree properties are violated again, because now the node 10 has a right child, which is red again, and no red node have a red child. So again, we have to fix a red-black tree. And this situation is the case 2 situation. We have to make a left rotation on node 10. After making a left rotation, again we have to check whether the red-black tree properties are violated or not. And as you see, it is violated because the 19 node 19 is a red node, and its left child, node 10, is red too. So no red nodes has a red child. So that's why the red-black properties are violated again. We have to fix it. And this is the case 3 situation. We have the node X here is the node 10. The node 10 is a left child because it is the left child of the node 19, and the uncle of node 10, the node 55, is black. So this is the case 3 situation. We have to make a right rotation on the node 10's grandparent. The grandparent of node 10 is node 32, the root node, so we have to make a right rotation on the root. Okay, and after the right rotation, our tree is a valid red-black tree. The root is black, and every red node has 2 black nodes, 2 black children. So it is valid, and as you can see, it is balanced. So all of the operations will have logarithmic time complexity, such as searching operation, removing operation, or insertion has logarithmic time complexity. And this is the aim of red-black trees and AVL trees, to make sure that these operations will have logarithmic time complexity. So that's all about red-black trees. Thanks for watching.